We'll begin with what sets this industry apart from all others, felting needles. Felting needles are produced from very specialized steel with unique chemical compositions. The first step in manufacturing needles is blanking. Coils of wire are straightened and cut into predetermined lengths. Precision dies rotating at high speed work the blank in swedging operations to yield single or double blade diameter reductions. In the next step, the working blade is changed from a round cross-section into a triangle with 3 apexes, a star blade with 4 apexes, or a pinch blade with 2 apexes. The crank, which positions and holds the needle firmly in the board, is bent and the barbs are formed or cut into the apexes at the exact locations required. The points are also formed on the needle. Different type points are used depending on the application. The final step is heat treating, where needles are hardened and tempered to ensure proper wear resistance and flexibility. Synthetic staple fiber can be made with polypropylene, polyester, nylon, aramid, acrylic, or polyethylene polymer. The choice of polymer depends on the physical properties desired in the finished product. Polymer in flake or pellet form, along with other additives, are fed by gravity into the extruder, where they are melted and mixed together into a uniform liquid. The molten polymer is evenly distributed to individual metering pumps and is pumped to the spinneret and through numerous small holes that determine fiber denier and cross-section. Fiber finish used to control static and fiber frictional properties is applied. Fiber polymers are made up of long-chain molecules. The molecules in the fiber at this point are best described as looking like a plate of spaghetti, without the sauce. This undrawn fiber is characterized by high elongation and low strength. The drawing stage straightens the molecules, causing them to line up next to each other, forming crystalline areas that enhance the fiber properties. The molecules at this point look like uncooked spaghetti still in the box. After drawing, the fiber is crimped and cut into the desired staple length and then baled. A typical needle punch process includes the following sequences: fiber opening, carding, cross-lapping, needle punching. The force used in the fiber baling process and the amount of time the fiber is in the bale cause the fiber to mat together into large clumps. The tightness and size of the clumps will adversely affect carding, so all baled fiber goes through some opening to break apart and reduce the size of the clumps. Whether it is an elaborate opening system or part of the card feed hopper, the more opening that is done before carding reduces the workload on the card. Here you can see a system that removes fiber from several bales at the same time. This not only begins the opening process, but acts as a blending system as well. It is desirable to feed from a large number of bales to minimize any bale-to-bale fiber variability. Precision blending systems are used to mix exact amounts of fiber in cases where color, deniers, or fiber types must be blended together. The most common opening is done with some form of bale breaker. Most opening lines have several bale breakers which are manually fed. Spike aprons lift the fiber, causing the clumps to fall apart. A beater system at the top of the spike apron removes excess material from the spikes, resulting in more fiber opening. The fiber is usually fed into some type of opener. This could be a simple pin roll opener with large pins or a fine wire opener that precards the fiber. Fiber can be opened too much, especially fine denier fiber that can be easily damaged from overworking the fiber. Opening increases the volume of the fiber, and at some point, that volume will restrict the pounds that can be fed through the feeder and into the card. From the opener, the fiber is pneumatically transported to a card feeder or directly into a feed chute. The purpose of carding is to separate, align, and deliver the fiber. Most cards are a series of rollers covered with sawtooth wire that rotate at different speeds and directions. Here are some typical examples of card wire. The height, angle, and coarseness of the wire can be modified for fiber type, length, and denier. Fiber is transferred from roll to roll by carding action, which is rolls turning in opposite directions, or stripping action, which is rolls turning in the same direction at different speeds. The carding action separates and aligns the fiber, while the stripping action moves the fiber through the card. This continuous transferal results in a fiber web consisting of fibers laying predominantly parallel to each other. The feed section compacts the clumps of fiber into a feed mat. This feed mat is fed into the card through the feed rolls, lickerin, transfer rolls, workers, strippers, and doffer. The webs are removed from the doffer by either a comb or doffing roll. Some doffing rolls are used to randomize the fiber coming out of the card, reducing the amount of paralleling. The web strength is much greater in the direction of the fiber than in the direction across the fiber, where the only strength comes from the fiber entanglement. Randomizing the web helps to balance the strength in both directions. Another type of card is a stationary carding plate card. These are a modification of cards used in a short staple yarn production. As the name implies, this card has no rolls but stationary carding plates. The sawtooth wire is attached to the surface of the plate. The web is now transported to the crosslapper. There are several purposes of the crosslapper. The simplest is to lay down the carded web to the desired width. Since the majority of cards are 2.5 meters wide, wider fabrics require the use of a crosslapper. The crosslapper continuously lays down the web on a floor apron running 90 degrees to the crosslapper. The floor apron is moving forward, resulting in the webs laying down at an angle. Since carded webs have more strength in the machine direction due to paralleling, laying the web down at an angle helps to balance the machine direction and cross-machine direction physical properties. Balanced physical properties are more critical in some product lines than others, while some products required unbalanced properties. Carded webs weigh between 1/2 and 2 ounces per square yard, so another purpose of the crosslapper is to build up the desired weight by controlling the number of layers in the back. A side benefit of having multiple layers is increased uniformity, since heavy or light areas in the individual webs tend to be evened out in multiple layers. Since crosslappers have to reverse direction, the speed of the laydown at the outside edges is different than in the middle. This results in fabrics that are heavier on the outside edges. Usually the outside edge is trimmed off and either scrapped or recycled. Crosslapper drive systems are continuously redesigned to improve the side-to-side weight variations, the latest being profile lappers, which have the capability of speed adjustment across the entire laydown width. This allows the operator to control speeds so that the weight can be adjusted across the width, eliminating heavy edges or lightweight middles. This hardly looks like state-of-the-art equipment, but it was just a few short years ago. Actually, this loom was built in 1952, and as you can see, it still runs. This loom has 38 needles per linear inch, which today would be low even for a tacker. You can see how simple the mechanism is, and the speed is close to maximum. Today's looms are approaching speeds of 2,000 strokes per minute and have needle densities over 100 needles per inch, and now are made with several boards that allow for densities over 450 per inch. The purpose of needle punching is to mechanically entangle fibers. As the barbs on the needles pass through the fiber back, they fill with fiber and transport the fiber from the horizontal to the vertical. Repeated penetrations of the needle entangles the fiber so that the finished fabric has the required physical properties. The needle passes through the stripper plate, fiber web, and bed plate. The bed plate supports the fiber so the needle will penetrate the web. The stripper plate forces the fiber off the needle so the web can be moved forward by the take-up rolls. It is important to get the needle in and out of the web as quickly as possible to minimize stretch in the fabric as well as the bending force on the needle caused by the moving fabric. Needle breakage is almost always the result of needle deflection. Needle looms today have elaborate feed systems to reduce the stretch required to move the bat through the loom. These systems include some form of bat compression and force feeding into the needling zone. You can see how the bat is compressed and how easily it moves into the needling zone. The needles then entangle the fiber. Some manufacturers use tackers to achieve the same result. Tackers are designed to compress the bat without excessive amounts of stretch, so that the bat can be fed into the needle loom. These looms usually have smaller needle boards and low needle densities. Today's feeding systems have given the manufacturer the luxury of eliminating tackers, saving floor space and dollars. This loom is an upstroke loom. The principles are the same, just upside down. The stripper plate is at the bottom and the bed plate is on the top. You can see the points of the needles just penetrating through the bed plate. This loom is used for an inline processing when the manufacturer wants to needle both sides of the fabric. Double-sided needling improves fabric strength. Some manufacturers use two downstroke looms to achieve the same results, but this requires threading the needled bat over and under the second loom in order to turn the bat upside down for needling. This loom has both upstroke and downstroke. This single loom takes up less floor space and usually costs less than two separate looms. Manufacturers have found the needling results of this loom to be different from two separate looms. The alternating up and down strokes entangle the fibers more than all downstrokes followed by all upstrokes. There are several looms on the market today that use especially designed needles to produce pile fabrics. These looms have evolved as the marketplace has accepted the products. The products opened new markets. The markets wanted modified products. The products required modified looms. The first structured looms, as they were called, was a basic downpunch loom that had a modified bed plate. Instead of holes, the bed plate was a series of spacers that allowed the pile to be formed in the spacer and stay in place so that further needle penetrations added to the pile that was formed. The pile is formed by needles that have a U-shaped fork in place of the point. The fork fills with the fiber and creates a loop that is pushed through the fabric. There were several limitations to the fabric produced. As you can see, the pile is produced in straight rows, limiting the structures to either a rib fabric or a high enough pile to cover the rows. This type loom required fabrics that were heavier in weight and strong enough to survive the force required to pull the pile through the spacers. High fiber denier was also required to minimize fiber breakage. The second generation loom addressed the weight issue by modifying the bed plate to a series of circular spacers. The bed plate now carried the fabric through the needling zones, eliminating the need to pull the fabric. The needle boards were smaller, and the needling was done horizontally instead of vertically. The needling was also done on the circumference of the cylinder, which resulted in slightly varying pile heights, giving the appearance of a fuller, richer pile. Carrying the fabric through the needle zones allowed the manufacturer to produce much higher piles with lower denier fibers. The third generation loom, or random velour looms invented by Delo Incorporated, addressed the issue of pile in rows. The loom was a standard downpunch loom, but the bed plate was now replaced by a brush conveyor that carried the fabric through the needling zone. The needles were modified to be similar to standard felting needles, but with one barb per apex and each barb equally spaced from the point. Each needle carries less fiber than the fork type, but this is balanced by the large number of needles and the increased number of strokes. The elimination of rows allowed for much shorter pile heights. All three types of looms are still used today, producing a wide variety of fabrics for several different marketplaces. After needling, fabrics are finished as needed. This could include slitting, calendaring, coating, laminating, printing, shearing, or just about any finish technique used in textile finishing. And just where are needlepunch fabrics going? Anywhere your imagination will take them.